Apart from a flat plane, all the other surfaces you can think of are curved to some extent. But can we say how curved they are? Can we quantify their curvature? Mathematicians have devised two measures of curvature, Gaussian and mean curvatures. I've talked about Gaussian curvature in a previous video, but I want to reintroduce it slightly differently to accommodate mean curvature into the picture. It's also because mean curvature is related to soap films, the maths of which is something that I want to talk about. But for now, let's focus on the two measures of curvature. These two kinds of curvature are defined at a point rather than the entire surface. Very roughly speaking, they characterize the rate of change of the normal vector. But how is this related to our normal intuition of how curved a space is? At first glance, this bump should be highly curved, and indeed, the normal vector changes a lot when we go over the bump. So with this quick change of normal vectors, under this rough mathematical definition, the Gaussian or mean curvatures should also be high. So in this case, the numerical values match our intuition that the curvature is high. On the other hand, for surfaces that look like this, intuitively it is quite flat, and the normal vector changes quite slowly across the surface, and so both curvatures should be quite small in magnitude. Again, we see a match between our intuition and the mathematical description of curvature. Now let's see this in a lot more mathematical detail of how to describe this rate of change. For any point on the surface, we can construct a normal vector. By construction, we normalize the vector to have length 1. This allows us to fit the normal vector neatly into a unit sphere. This process of associating a point on the surface to a vector on a unit sphere is called the Gauss map. In general, different points on the surface can have different normal vectors. To investigate a little more deeply, let's say we nudge the point on the surface slightly in the direction of the vector v, so that we arrive at this slightly displaced location. Then we can see that the normal vector changes, with the old one pointing vertically upward and the new one pointing to the side. Over on the other side, we gather these normal vectors to fit on the sphere. So when you nudge your location at a velocity of v, your normal vector also changes at some velocity. Let's call this w. This w changes if you change v, your initial nudge, in direction. So in addition to the Gauss map, we can think of going from a change of point on the surface to a change of vector to the sphere. This map is called the shape operator. In this example, v and w seem to be pointing in the same direction, but they don't have to. Let's see an example where this isn't true. Enter the cylinder, and pick a point on it, and consider the normal vector at this point. We collect this normal vector on the sphere on the right. Back to the cylinder on the left, we consider a slight nudge along the cylinder towards this yellow point. However, at these two locations, the normal vectors are exactly the same. This means that if you nudge this point along the cylinder in the direction v, the resulting change in the normal vector, the corresponding w, is 0. However, if we change the location by going around the cylinder instead, so v points into the screen, initially the normal vector points upwards, and as we go around the cylinder, the normal vector goes around as well. So if the initial nudge on the surface is in the direction v, then the change in the normal vector is also in the same direction. In this illustration, it seems that v and w are the same, but they don't have to be. After all, if the radius of the cylinder is larger, even with the same nudge, the normal vector wouldn't change as much, and so the w would have been smaller in magnitude. It still points in the same direction though. However, if we were to nudge in some oblique direction, not around or along the cylinder, because the normal vector can only lie on this circle, the corresponding W can only be in this direction. As a summary for the cylinder, if we denote S as the shape operator, and V is along the cylinder, then the resulting W, or S of V, is 0, because the normal vector doesn't change along this direction. If V is going around the cylinder, then W is pointing in the same direction. And if V is some oblique direction, W is still pointing in that previous direction into the screen. These cases all suggest that the shape operator simply projects V onto a particular direction, potentially followed by stretching or squishing along the direction. That's just the cylinder, but in general, for all regular surfaces, the shape operator is a linear map. Technically, these V and W are vectors in 3D, but it turns out that S can be viewed as just a 2D linear transformation. How? Well, when you move your location on the surface, the initial velocity vector V must lie on the tangent plane, and by definition, the normal vector is perpendicular to the tangent plane. This normal vector goes over to the sphere by the Gauss map. But now the vector is perpendicular to the tangent plane of the sphere. Those W's have to lie on this tangent plane because they are the change of this vector. So we can see that both of these tangent planes are perpendicular to the same normal vector. This means that the two tangent planes are actually parallel to each other. So V and W lie on effectively the same plane, and the transformation from V to W can be thought of as just a 2D linear map. For a cylinder, if you choose to align your basis vectors such that 1, 0 is along the cylinder and 0, 1 lets you go around the cylinder, then because the shape operator in this case is a projection onto the 0, 1 vector, the matrix representation in this basis only has one non-zero entry. The first column being 0 refers to the normal vector not changing when you go along the 1, 0 direction, and the second column refers to the normal vector changing in the same direction as 0, 1. However, in linear algebra we know that a matrix representation depends on our choice of basis vectors. If we have chosen a different basis, then the matrix representation doesn't look like that anymore. So are there any quantities associated with the shape operator that don't depend on the choice of basis? For a 2x2 matrix, the two main basis independent quantities are determinant and trace. For the determinant, Gaussian curvature is precisely defined as the determinant of the shape operator, and the mean curvature is defined as half the trace. In the case of a cylinder, we have shown that in one basis, the matrix representation looks like this. So the Gaussian curvature of a cylinder is 0, and the mean curvature is some non-zero quantity that depends on the radius. The cylinder is just a toy example to illustrate these two curvatures. What happens for more general surfaces? Is there a general procedure? For a general surface, we can always describe it with two coordinates, at least locally. For example, the sphere can be described with spherical polar coordinates, and the cylinder can also be described with two coordinates. In general, given this coordinate description of the surface, there are two natural tangent vectors we can construct. Those are the partial derivatives of phi with respect to the two coordinates. You can think about them as a nudge of the current location in the direction of increasing u or v. If u slightly increases, partial phi partial u is the direction in which you move. Similarly, partial phi partial v is the direction you move when you slightly increase v. If these two directions are not parallel, they naturally form a basis of the tangent plane. On the other hand, at each u and v, we can in principle compute the normal vector at the point phi of uv. For example, we can compute it by the cross product of phi u and phi v, which will be perpendicular to the tangent plane, and then we normalize it to have length 1. What does the shape operator do to the two basis vectors? Upon increasing u, the position on the surface changes at the rate phi u. Then at the same time, upon increasing u, the normal vector n also changes at the rate nu. So the shape operator sends phi u to nu. Similarly, if we increase v instead, we get that the shape operator sends phi v to nv. So if we choose our basis vectors to be phi u, phi v, what should be the 2x2 matrix representation of the shape operator look like? The first column should denote the coefficients of nu written in this basis, and the second column denotes the coefficients of nv in this basis. Now it is simply a matter of finding these coefficients, and here is what I would describe as a trick. One way to write these two equations is to make it into a matrix vector form. This is not your standard matrix transformations, but it serves as a shorthand for the two equations. We can check that nu in this matrix notation does equal a phi u plus c phi v, and the nv in this shorthand notation does equal b phi u plus d phi v. The matrix in this notation is precisely the matrix representation of the shape operator, so we can replace this matrix by S. The next step is a bit tricky. We somewhat multiply both sides on the left by a kind of column vector phi u, phi v. This is similar, but not exactly the matrix multiplication you see. All these multiplications are dot products, which means if we expand everything, all the matrix entries are dot products. If this manipulation seems a bit dodgy, you can always go back to the original two equations and dot both of those with phi u and phi v. This is just a bit of a shorthand notation for convenience. Going back to this matrix equation, the matrix on the right is usually denoted with the Roman numeral 1, short for first fundamental form, and the matrix on the left is denoted with the Roman numeral 2, short for second fundamental form. Notice that both matrices 1 and 2 are ordinary matrices now, in the sense that each entry is just a real number. So we can say that 2 equals 1s, and hence s can be solved as 1 inverse 2. After solving for s in matrix representation, you can obtain Gaussian and mean curvatures with its determinant and trace. These matrices 1 and 2 seem to be tedious to compute, let alone taking the inverse, and in general they are. But these are just to help us solve the system of equations. If we know nu, nv, phi u, phi v, this is a general procedure to solve for a, b, c, d. If you can solve these a, b, c, d by inspection, you don't need all this fuss. Like what we did for the cylinder, we can just do inspection to find the matrix representation without the first and second fundamental forms. Now that we know the relationship between these curvatures and the shape operator, the curvatures do characterize some sort of rate of change of normal vector, because the shape operator is really about the change in the normal vector. In the beginning, we noticed how this idea really reflects our intuition and what we discussed is just a way to formalize what we mean by curvature, making it more precise. One thing though, previously we defined mean curvature as half the trace of S. Why is it called mean? I've made a second channel video to answer that question. The next main channel video will be about how mean curvature is related to soap films, and the one after that will find all possible shapes of soap films. But for now, if you don't know already, the Summer of Math Exposition contest will be run by the community this year, so there wouldn't be any prizes this year. I thought it would be nice for me to shout out some of my favorite videos this year, and I have outlined my criteria in picking my favorites, linked in the description. As always, don't forget to like and subscribe, and I will see you next time.